Hi, I'm Patty Schwarzkopf. Today I'm meeting with one of my students to talk about symmetry and transformations. Please join us. We'll determine whether a graph is symmetric with respect to the x-axis, the y-axis, and the origin. We'll also determine whether a function is even, odd, or neither even nor odd. Finally, given the graph of a function, we'll graph its transformation under translations, reflections, stretchings, and shrinkings. Now let's begin by talking about symmetry. Symmetry deals with mirror images. If we were to draw an imaginary vertical line down the front of the typical human body, we would see that each eye is about the same distance from the bridge of the nose, each ear is about the same distance from the bridge of the nose, each shoulder is about the same distance from the center of the chest, etc. Can you think of any other situations in which we deal with symmetry?
Well, perfect examples in sports. Well, one is football. If you're on the 50-yard line, you have the end zone on each side, and also in basketball, if you're half court, the same distance on each side of the court.
Very good. That's very good examples of symmetry. Sometimes graphs exhibit symmetry. Let's talk about how graphs can exhibit symmetry. If for any point x, y on a graph, the point x negative y is also on the graph, then the graph is symmetric with respect to the x-axis. X equals y squared produces a graph that's symmetric with respect to the x-axis. We see that this graph contains a point 4, 2 and also a point 4, -2. Now, algebraically, we can determine whether this graph is symmetric with respect to the x-axis by replacing y with the opposite of y in the equation. If I simplify and get an equivalent equation, then I know it's symmetric with respect to the x-axis. So if we were to replace y with the opposite of y, so in other words, look at x equals the opposite of y squared, and simplify, we would have x equals, when I simplify the opposite of y squared, I have y squared. I have an equivalent equation. So since that happened, we can verify that this is symmetric with respect to the x-axis. If for any point xy on a graph, the point negative xy is also on the graph, then the graph is symmetric with respect to the y-axis. So y equals x squared minus 5 produces a graph that's symmetric with respect to the y-axis. We see that we have the point 3, 4 on the graph, and we also have the point -3, 4 on the graph. Now, algebraically, we can determine that this represents a graph, or will give a graph that's symmetric with respect to the y-axis if I'm able to replace x with negative x, or the opposite of x, and be able to come up with an equivalent equation. So if we replace x with the opposite of x, we would have y equals the opposite of x squared minus 5. And when I simplify here, the opposite of x squared is just x squared minus 5, and we have the two equations that are identical. If for any point xy on a graph, the point the opposite of x, the opposite of y, is also on the graph, then the graph is symmetric with respect to the origin. Here's an example. X squared equals y squared plus 2 produces a graph that's symmetric with respect to the origin. We have a point 3, square root of 7. We also have a point the opposite, or -3, negative square root of 7. Now, we can determine algebraically whether this equation is going to give us a graph that's symmetric with respect to the origin if we're able to replace x with the opposite of x and y with the opposite of y and have an identical equation. So let's work with that. This is the original equation. If we were to replace x with the opposite of x and replace y with the opposite of y and simplify, we would have the opposite of x squared is x squared, the opposite of y squared is y squared, plus 2. We have an equation that's identical to the original equation. All right, let's work a few problems here. First, we'll graph the equation and determine visually whether it's symmetric with respect to the x-axis, the y-axis, and the origin. And then we'll verify the assertion algebraically. So the first thing we want to do is look at the equation 5y equals 2x squared minus 3 and graph it use a grapher to determine a graph. So let's do that first. Now, before we put it into the grapher, we do need to solve for y. So if I were to solve this for y, I would have y equals 2/5 x squared minus 3/5. So I'll need to do that in order to enter it into the calculator. So let's go ahead and do that. Press the y equals key and enter y equals quantity 2/5 x squared minus 3/5. And now we'll need to set the window, but I believe a standard viewing window would be fine here. So I'll press zoom 6 for the standard window. And here's the graph. Now it appears that the graph is symmetric with respect to the y-axis. How can we verify that algebraically?
Well, for symmetry, can't we just take the opposite of x, or negative x?
Yes, replace x with the opposite of x and see if we get an identical equation. And that's for y-axis symmetry. So let's take a look at the original equation. And what we'll want to do is to replace x with the opposite of x. So we have 5y equals 2, and again I'm replacing x with the opposite of x, squared minus 3. So we have 5y equals 2. Now simplifying this, the opposite of x squared is just x squared minus 3. And that is identical to the original equation, so we see that that verifies our result, that it is symmetric with respect to the y-axis. Now the next graph we need to look at is y equals 1 over x. So we'll go back to the grapher, press y equals, and clear out the previous equation, or the previous expression, and we'll put in 1 divided by x. And let's see what happens. In this case, I'm going to change the window. I'm going to use a window that goes from -5 to 5 on the x-axis using an x scale of 1, and -5 to 5 on the y-axis also using an x scale of 1. And let's press the graph key. And it seems that the graph is symmetric with respect to the origin. If the graph is symmetric with respect to the origin, then we should be able to replace x with the opposite of x and y with the opposite of y and have an equivalent equation. So if we were to do that, replace y with the opposite of y and x with the opposite of x, we would have the opposite of y equals -1 over x. And if we were to multiply each side by -1 or divide each side by -1, whichever you prefer, we would have y equals 1 over x. And that's identical to the original equation. Now in these examples, the first one was symmetric with respect to the y-axis. If a graph is symmetric with respect to the y-axis, we say that the graph is representing an even function. And if the graph is symmetric with respect to the origin, as we saw in this case, we say that the graph represents a function that is odd. So we're talking about even and odd functions. An even function, again, produces a graph that's symmetric with respect to the y-axis, and an odd function produces a graph that's symmetric with respect to the origin. So let's go ahead and test algebraically whether the function is even, odd, or neither even nor odd. Then check the work graphically using a grapher. Now, before I do that, we can say that a function is even if f of x equals f of the opposite of x. And we can say that a function is odd if the opposite of f of x equals f of the opposite of x. So the opposite of f of x equals the f of the opposite of x. So what we'll need to determine here in order to come up with an answer for this is to calculate or determine f of the opposite of x and the opposite of f of x. F of the opposite of x equals negative 3 times the opposite of x cubed plus 2 times the opposite of x. So we have negative 3 times negative x cubed minus 2x, and that equals 3x cubed minus 2x. So f of the opposite of x equals 3x cubed minus 2x. Let me just rewrite that here. Now let's determine the opposite of f of x. That's just the opposite of negative 3x cubed plus 2x. So that equals 3x cubed minus 2x. All right. So let's see what happens then. For even, once again, we want to know, is f of x the same as f of the opposite of x? Well, f of x equals negative 3x cubed plus 2x. Is that the same as, remember, f of the opposite of x is 3x cubed minus 2x. Are they the same? No, they're not the same. So the answer is no. It's not even. Let's determine if they are odd. If they're odd, then we would say that the opposite of f of x equals f of the opposite of x. Well, the opposite of f of x is 3x cubed minus 2x. Is that the same as f of the opposite of x, which is 3x cubed minus 2x? And of course, they are identical, so the answer is yes. We have an odd function here. We can check this graphically then. Let's use a grapher. We'll press y equals, and we'll enter the function. The function is negative 3x cubed plus 2x. And we'll use the window that we had set previously. X is going from negative 5 to 5, and the y is going from negative 5 to 5 as well. And when we press graph, we see a graph that is symmetric with respect to the origin. We could trace and find a couple of points to verify this. For example, we have the point 10638.298, comma 0.209154004, and if we go the other way, we have negative 0.106383 and negative 0.209154. So you can find many points that fall into that same pattern. Now, we want to be able to quickly sketch a graph by shifting what we call basic graphs horizontally, vertically, stretching them, and shrinking them. Before we can do this, we have to review some of our basic graphs. We have the squaring function. It's a U-shaped graph. It's a parabola. We have the square root function. We have the cubing function. We have the cube root function. We have the reciprocal function. We recently took a look at that one. We have the absolute value function. Now, these graphs are very commonly used graphs, so these should be in your head. You should have a visual image of these graphs. Now, what we're going to do is work with these graphs, and we're going to possibly work with vertical translations. And when we do that, for b greater than 0, the graph of y sub 2 equals f of x plus b is the graph of y sub 1 equals f of x shifted up b units. The graph of y sub 3 equals f of x minus b is the graph of y sub 1 equals f of x shifted down b units. So what we're saying here is that if you have a function f of x, all right, in each case we're dealing with that basic function, if you add a constant to that function, all that does to the graph is shifts it vertically. So if you add a positive constant, it will shift it up that number of units, and if you add a negative constant or subtract a constant, it will shift it down that number of units. Now let's look at horizontal translations. For d greater than 0, the graph of y sub 2 equals f of the quantity x minus d is the graph of y sub 1 equals f of x shifted to the right d units. The graph of y sub 3 equals f of the quantity x plus d is the graph of y sub 1 equals f of x shifted left d units. So notice a difference now. We're replacing the input with a quantity x minus or x plus. Now, if you're and remember, d is a positive number. So if you're replacing in your original function the input with x minus a constant, you're shifting to the right. And if you replace it with x plus a positive constant, you're shifting to the left. The graph of y sub 2 equals the opposite of f of x is a reflection of the graph of y sub 1 equals f of x across the x-axis. So you're basically replacing y with the opposite of y, f of x with the opposite of f of x, and you get a reflection across the x-axis. The graph of y sub 2 equals f of the opposite of x is a reflection of the graph of y sub 1 equals f of x across the y-axis. So we're taking the basic graph, reflecting it across the y-axis if we're replacing the input with the opposite. The graph of y sub 2 equals a times f of x can be obtained from the graph of y sub 1 equals f of x by stretching vertically for the absolute value of a greater than 1 or shrinking vertically for the absolute value of a between 0 and 1. In other words, the absolute value of a greater than 0 and less than 1. Okay, let's take a look at an example. Let's see what would happen to the graph of the function f of x equals negative 1/4 times the quantity x minus 5 squared. Now what we're basing this on is a graph, I'll call it f sub 1. F sub 1 of x equals x squared. So we're basing this on the squaring function. And what we've done is replaced the input with x minus a constant, so that's going to represent a horizontal shift. We've also taken the opposite of this function, so that is going to give us a reflection in the x-axis or across the x-axis, and because of the constant, the constant of 1/4, we're going to have a shrinking then by a factor of 1/4. So if we were to look at this, now what we expect to do again is see that U-shaped graph shifted 5 units to the right, reflected across the x-axis, and shrunk. Let's take a look at that graphically. So press your y equals key, clear out the last function, and let's enter this. We have negative 0.25, or negative 1/4, times the quantity x minus 5 squared. And let's use a window. Let's use the window where the x-mins go from negative. The x-min is negative 5. The x-max is 20 with your x scale of 1. Your y-min is negative 10. Your y-max is 10 with a y scale of 1. And here we see the graph. It's a U-shaped graph, the graph of the squaring function, shifted 5 units to the right, reflected across the x-axis, and shrunk by a factor of 4. By a factor of 1/4. All right, let's try another problem. Write an equation for a function that has a graph with the given characteristics. Check your answer using a grapher. We're going to use the shape of y equals the square root of x, but reflected across the y-axis and shifted to the left 2 units and down 1 unit. All right, let's see what we have then. All right, first we have the reflection across the y-axis. And remember, we're working with a function the original function, y equals the square root of x. So if we're reflecting that across the y-axis, then the function would look like y equals the square root of the opposite of x. If we shift left, two units, we would have y equals the square root. Remember, we have the opposite there, and we're replacing this now, this x, now with x minus 2, excuse me, x plus 2, because we're shifting to the left, so we want x plus 2 inside the quantity. And shift down 1 unit, we would just take y equals the square root of the opposite of x plus 2, and to shift down 1 unit, we'll just subtract 1 from the function. And now we just need to simplify this. So we have y equals the square root of negative x minus 2 minus 1. And then we can check that on the grapher. So let's take a look. We'll press y equals and clear the last function. We'll enter the square root of the quantity, negative x minus 2, and subtract 1 from that. And the window I'll use is negative 5 to 5 on x, and negative 5 to 5 on y, with your x scale and y scale being 1. And now press graph. We can see that this graph is the graph of the square root function reflected across the y-axis, shifted left 2 units and down 1 unit. Now today we talked about symmetry and transformations. We talked about symmetry with respect to the y-axis, with respect to the x-axis, and with respect to the origin. We talked about even and odd functions, and we also talked about transformations. Make sure to review all your notes before you begin the exercise set, and good luck with your work.